Welcome to Brain Vision.
To solve this problem, let's first begin to understand it conceptually. If we look here to the right, we see the problem drawn out in a Cartesian plane, where we have a moving charge particle, which is our negative charge particle, which would be our electron moving in the Vx direction up on the y plane. And then we have here the origin point, right, which is a 90 degrees to this. And then also we have a proton, a positive charge particle moving in the Vy plane. And we have the distance between them, between the origin point and the electron as A, and the origin point between the proton as B. This is the distance between those two, where A is equal to 5 nanometers, 5 times 10 to the minus 9 meters. B is 4 times 10 to the minus 9 meters. We can solve for R, the distance between the electron and the proton, as that hypotenuse, which would be equal to the square root of A squared plus B squared, which is 6.4 times 10 to the minus 9 meters. To understand how to draw these magnetic fields, we can look at the image I've drawn here, where we have a charged particle moving in the x hat direction, right? And we have an origin point here, right here as r, which is our vector, which is our distance vector. And we see that the magnetic field would be perpendicular to these in the z direction. And it's moving, as you can see, in our blue arrows. Now, how do we draw that? Well, we know that the magnetic field is perpendicular to the velocity vector. So the velocity is going into the page. So imagine it going into the page. Then the magnetic field would circle around this, right? And so in a clockwise direction. And this would be just based on the right-hand rule that you've learned previously. Now, we know that as we can draw these planes out, right, as the vectors, we have our unit vectors, which is our z hat, x hat, and y hat. The magnitude of each of those unit vectors is equal to 1. And here below we have here some of the constants we need to take into consideration, which is our magnetic permeability, our dielectric permittivity, and our fundamental charge. And then we know that Q of E, which is our charge of the electron, is just equal to the minus our elementary charge, and then the proton is equal to plus our elementary charge. And so to solve this problem, if we look at the Biot-Savart law, we see that the magnetic field is nothing more than a moving charge, right, perpendicular to some r distance divided by r squared. This is our Biot-Savart law. So to finish our setup on this problem, what we want to do is be able to solve for these angles. These will come into handy a little bit later, but let's solve them right now to get them out of the way. We know that the sine of this angle, which is our electron angle, is equal to B, right, divided by our hypotenuse R. So we can write theta of E is equal to the inverse sine, and this is going to be our 4 nanometers. Let's make that a little bit better. So this is 4 nanometers divided by 6.4 nanometers. And so theta of E is going to be equal to 38.7 degrees. And here we know that we can take theta of E plus theta of P, and this is going to be equal to 90 degrees. Here we can plug this into here and solve for theta of P as 51.3 degrees. This will come in handy later, because now we can take the Biot-Savart law for the first part of the problem, right? And so part A is asking us the total magnetic field of the contribution of the electron to a point origin, and then the contribution of the proton to the origin point. So B total is going to be equal to Bx x hat plus By y hat, right? And so we want to solve for Bx and By. So setting this up, we know that we can write this equation, the magnitude of B, in the form of u hat 4 pi, and then this will be equal to q v sine theta over r squared. So B of x, the magnitude of B of x, is going to be equal to u naught 4 pi, and this would be plus E, right? Since it's a positive charge, times V times V, and then there'll be sine theta over r squared, where we can, this will be u naught 4 pi E cross V, and here this theta is going to be equal to that 90 degrees. So sine theta is equal to 1. So all we have here is E times V, B squared. Plugging each of these in, we know the value for each of these. We can get this as, we solve this as 5.41 times 10 to the minus 4 Tesla. Repeating this again, By, we get u naught 4 pi, and now we have a minus E, it's a negative charge. However, we are going in the minus y direction, right? But this is just going to be a minus 1 since we're taking the magnitude of these unit vectors, and that's what we're trying to solve for. So these will eventually cancel out to give us a positive value. And then you have V sine theta all over a squared. This will give you u naught. This is just going to be equal to 1. U naught E V sine theta over a squared. This again, we have theta is equal to 90 degrees to the origin. So sine theta of 90 equals 1. So going back here, we can plug in each of these values, right? And so B of y is going to be equal to 8.46 times 10 to the negative 4 Tesla. Knowing both of these, we can write that the total magnetic field from each of those contributions is going to be equal to B of x plus B of y, right? And so this is going to be equal to 5.41 times 10 to the minus 4 Tesla plus 8.46 times 10 to the minus 4 Tesla, which gives us a total magnetic field of 1.39 times 10 to the minus 3 Tesla. So that was for part B. For part A. For part B, we are asked only the contribution, right? So let's go back up here. So for part B, we want to find this magnetic field, right? So this is between the electron and the proton. To do that, now we can write the Biot-Savart law. Sorry. So we can write that as B is going to be equal to U naught 4 pi. And then we have Q times V sine theta divided by that R squared. And this time we're going to be using the distance between these two, and theta is actually going to be equal to that theta of P that we solved for. If you remember, that is 51.3 degrees. So knowing this, we can put this as U naught 4 pi. And then what we have here is 1.602 times 10 to the minus 19 C times our velocity, which was 845 times 10 to the 3 meters per second. And then we'll have sine of 51.3 degrees, all divided by 6.4 times 10 to the minus 9 meters squared. And this gives us 2.58 times 10 to the minus 4 Tesla. So that was for part B, which was the magnetic field at the point of the proton from the electron. So part C is going to be asking about the electric field, about the force of the electric field to the force of the magnetic field. Now, what we know here is that the electric field force is going to be equal to Q times E, which is our electric field. And so we can write this as Q, and then our electric field is going to be equal to 1 over 4 pi the dielectric permittivity, vacuum permittivity, times, and this would be Q2. Those are both our charges over R squared, and this would be in the R hat direction. For our case here, we can solve this as equal to 1 over 4 pi E naught, and this would be that E squared all over R squared, where in this case the R is equal to 6.4 6.4 times minus 9 meters. Plugging in each of our numbers for each of these as we have the constants above, right? And so what we know the E, we know the E0, and we know the R. Putting in here, we get 5.62 times 10 to the minus 12 newtons. We can also solve for the magnetic field, the force of the magnetic field, which is going to be equal to Q V cross B. So that's going to give us Q V, and then we have B defined here in terms of Q V sine theta R squared. And then remember, we have that U naught over 4 pi. Working the math out here, we can get that this is equal to U naught 4 pi E squared V squared over R squared. Plugging in each of the numbers, we get that this value is equal to 5.63. Oh, sorry. Plugging in each of these, we get that the value is going to be equal to 5.29 times 10 to the minus 23 newtons, which is honestly negligible, and we can approximate to 0. And so the final answer is going to be that the electric field is the dominating force. The electric force is the dominating force here, which was about 5.62 times 10 to the minus 12.